have the same time to reach the closure of the catchment. So let me make a sketch of the catchment. And let me suppose that the first isochron line is here. And let me use, okay, the same symbology that I used in the slides. And let's suppose that I call the time required to the drops that are lying over this line to reach the closure, let me call it delta t. Okay, that's fine. Let's suppose, for instance, that this is 1 hour. So, if this is the isochron line that corresponds to delta t, it means that all the points that are comprised between this isochron and the closure have a travel time that is lower than delta t. Good. Let now me draw the second isochron, like 2 delta t, and then let's suppose that we have the 3 delta t here. And let me suppose that the concentration time of the catchment is 4 delta t. Okay, that's good. Now, let me suppose that a rainfall event occurs over the catchment, which is given by a given yetograph. And let me assume that the yetograph is given by, let me use the same symbols, I over t. I over t, I prefer to explicitly recognize the dependence of I over time, so let me say it over t. And then let me suppose that the hydrograph is given by this event. And the time step is delta t. And when we apply the time area method, we usually draw the isochrons by using the same time step to which rainfall is observed. So it's not a coincidence that I depicted the yetograph by using the time step delta t, which is the same time step that separates subsequent isochron lines. Okay, and let's suppose that this yetograph occurs over the whole catchment. So spatial variability is neglected. Now, what happens over this catchment? And let's suppose, first of all, that at time 0, at the beginning, time 0 is here, at the beginning of the yetograph, you have the river flow that is equal to 0. This is an assumption that you can easily remove, but it's simplifying. So, especially if I have to write on the blackboard, it's simplifying. So let me assume that. And let me write down in a table here the time and the resulting river flow. So I said at time 0 the river flow is 0. Good. Now what happens over this catchment? It starts raining, and what happens after 1 hour? After 1 hour of rain, after 1 hour you got the intensity I1, or let me say I0. It's I0 here. Yes, I0. So, after 1 hour you got over the whole catchment the rainfall intensity I0. Now, if you look at this picture, you realize that all the drops that fell into this area, which I call A1, or let me call it delta A1. So all the drops that fell over this area reached the closure. Therefore, I can say that the river flow at time 1 is given by I0 times A1. Look, in writing this, you are applying the rational form. Only over this area. But it is the rational formula, because in the rational formula there was an assumption that I mentioned to you, that the whole catchment is contributing to the river flow. In this case, the model is a bit more complicated and assumes that after 1 hour, only this part of the catchment, the area delta A1, contributes to the river flow. But if you just make this difference, you can compute the river flow in the same way. There is another difference, which is the lag here of the runoff coefficient. So, really, we should probably write here also the C here. But in the representation of the time area method, to simplify things, usually people don't write explicitly C and assume that the rainfall is given by the so-called net rainfall, which means that C is already included in I. I hope this is clear. So just be aware of the difference. You can use what is called gross rainfall, pioggia lorda in Italian, and then you need to use the runoff coefficient. Be patient, the noise will slow down in 5 minutes. Or you can use the net rainfall, and you don't need then to use the runoff coefficient here. So usually in the textbooks, people say, when applying the time area method, that they use the net rainfall. It's just a matter of agreeing how to write it down. Okay, fine. Anyway, if you assume that you are using the net rainfall, then at time 1 you have this value of the river flow. Okay, let's move to time 2. At time 2, what happens? And I just need your attention for 30 seconds. At time 2, the situation is different, because you have the rainfall I1, occurring, which means that at the end of the second hour, you have the area delta A2 that is contributing to the river flow with the rainfall I0, and the area delta A1 that is contributing to the river flow with the rainfall I1. So basically your river flow is given by I1. Here, sorry, I forgot a delta. Okay. So I have I1 delta A1 plus I0 delta A2. This is the river flow. Okay, and then you can move forward. The only thing that you have to always take into account is correct placement of these subscripts. Okay, so basically you see here I0 delta A1, I1 delta A1 plus I0 delta A2.
Can you repeat the last one?
Sorry?
Can you repeat the last one?
This one? Okay, basically, when you get the second impulse of rain, the second hour, and we look at the end of the second hour. At the end of the second hour, you have this rainfall, I1, which occurred over the whole catchment. You get only the part of it at the closure that fell into the first area. Because this rainfall started here, and you look at here, 1 hour passed. So this rainfall, you got it only for this part of the catchment. But you had this rainfall 2 hours ago. And 2 hours ago, this rainfall started here, and you look here, 2 hours passed. So basically, you get the rainfall in the second hour that fell here 2 hours ago. Yeah, I know it's not so.
Yeah, for example, I'm for when I have the 4-hour distribution, for example, when I have 4 hours of rainfall, yeah, I still have in the closure the first I0 or.
No, after 4 hours, yes, you still have I0 from this area here.
Even if 24 hours?
Yes. It's after 5 hours that you don't see anymore the rain I0, because the rain I0 fell over the whole catchment. So at time, let's say 0, you get a drop here, and this drop takes 4 hours to get here. So for 4 hours, you are still waiting for this drop. After 4 hours passed, then you don't wait any more drops. You don't wait for any more drops. So basically after the time of concentration passed from rainfall, you don't see that rainfall anymore. So basically if you have rainfall starting now, you are expecting the effect of this rainfall lasting in the future during the whole concentration time of the catchment. So if the catchment has a concentration time of 15 hours, you are expecting to see the effect of the rainfall for the next 15 hours. After 15 hours, you don't see effect of rainfall anymore. Basically, we can move forward here. So let me refer to the third hour. The third hour, you have I2 delta A. Let me think to it. Delta A1 plus I1 delta A2 plus I0 delta A3. This representation is valid until you reach the time of concentration. Now let's try to condense this relationship by using a summation, like it is done here. You see, here basically it is written that the number of steps n is indicated like as Tc divided by delta t. So let me define this n here. N equal to Tc. Tc is time of concentration, and then at the denominator we use delta t. So n is the number of steps for which this representation is valid. And then you can write the river flow by using a summation. So let me write Q, and I want to use the same symbols. Okay, first of all, I don't like this QP, because I used QP to indicate the peak flow. This is not a peak flow. So basically QP, I don't like it. Let me write something like QT, okay? And this is equal to K summation k equal to 1 to n of what? Let's look here. Let's look at the summation. We have A increasing from delta A1 to subsequent values. So let me write here delta AK. And delta AK is multiplied I n minus k. Let me see if it works. In this case, let's suppose that k is equal to 3, because I want to write the summation. Then I have A1, which multiplies, we say that k is equal to 3, n is equal to 3, I3 minus k1, I2. Fine. Plus, k now it takes the value 2. Delta A2, delta AK, delta A2, fine. I n 3 minus k2, I1. Perfect. So, this is the representation of the time value method. And
sorry, you said it's the representation of time. I'm talking about, you said it's a representation of.
This is, let's say, it's the relationship that gives to you the river flow for subsequent time step. So there is still an incoherence here with the use of t, because here we have a q that depends on t, and on the right hand side we don't have any dependence on t. So this is not correct. Let me say that here we should say qn. We should say qn here, and but in this way we get only the value of the river flow for the value of n. Instead I want something varying from 1 to n. So let me use, let me write it in this way. Sorry for changing. Qt, and here I have to use t instead of n, and this is valid for t equal to 1, comma, n. Okay, this is correct. So this is the representation, to reply to your question, of the river flow at time t. And this representation is valid for t varying from 1 to n, where n is given by the time of concentration divided by the time step. And I'm not sure that I have to correct this slide. So it's not correct, because you see on the right hand side there is QP, and which means that Q depends on P, but on the left side, sorry, on the right hand side there is no P, so it's not coherent to write a relationship in that way. Because you see that the left, again I repeat, the left side says that Q depends on P, but if Q depends on P, then you should find the P value on the right side. It's not there, so it's not formally correct. This is a slide that I took from a colleague, and I didn't notice until now that it's not correct. The correct one is this, okay? Because you see here you have the dependence on Q over T, and you see T on the right-hand side. Otherwise, something is incoherent in the relationship. Is it clear what this relationship, how it was derived? Basically, this model assumes that the formation of the river flow is given by a simple transfer of rainfall along the catchment. So the question could be, is this model physically based or not? Or it's empirical? First, let me say that the model is linear. Look, you have a linear relationship between rainfall and river flow. It's a linear combination. What is written here, you see, river flow depending on what? Rainfall. And it's a linear combination of rainfall. And the coefficient of the linear combination are the delta A. So it's linear. So if the model is linear, you may say, yeah, this is not really physically based. It's empirical. On the other hand, as I said, this model basically operates a transfer of rainfall over the catchment. So you can recognize a mass balance here.
Sorry.
I repeat?
Yes.
Yes, fine. As I said, this model is linear, so starting from this consideration, you may say that it's empirical. On the other hand, as I said, this model operates a transfer of rainfall over the catchment. And the transfer is done according to a given mechanism and according to these isochrones, to the position of these isochrones. So if it is a transfer of mass, you recognize the conservation of mass concept here. You don't have more river flow than rainfall, it's a conservation of mass. And pay attention, you can also recognize here some energy concept, some conservation of energy. This is a bit difficult to see, but it's there. Why? Because when you draw the isochrones, you are making assumptions on the travel time. And therefore, you are making assumptions on the transport of the drop over the catchment. And this transport occurs through an exchange of energy. Potential energy of the drops that falls in the upper part of the catchment, and this potential energy is transformed in kinetic energy, and the drop travels. So when you define these isochrones, even if you don't realize it, because you are defining them empirically, but when you define these isochrones, you are referring to energy transformation. So there is the use of some dynamics here, energy. We don't care much, but as I said, it's important that we keep in mind it. So this empirical model is not contradicting the physics, absolutely. Okay, I hope it is clear, this representation, and but if it's not, I'm now making some further considerations and then I'm stopping for 15 minutes. If it's not clear, after the break, please ask me. And now, the considerations. I think you now understand why I showed to you 3 slides on the computation of the time of concentration. Because you need this empirical relationship to locate the isochrones. and to identify this delta A's, first of all. Second, keep in mind that here, this relationship I said, it's valid until I get to the time of concentration. And also, I assumed that the yetograph is lasting 4 hours, which is the exact duration of the time of concentration. Okay, let me say that actually this relationship is very general, because you may have 0 rainfall during a time step, and it works anyway. So you don't need that rainfall is different from 0 and has the same duration than the time of concentration. You may have 0 rainfall somewhere, and the rainfall could be longer, no problem. And even this relationship here can be used for times longer than the time of concentration. But you have to take into account that the delta A becomes 0 when you reach the time of concentration. So if you assume that for longer times than the time of concentration, the delta A becomes 0, and you have whatever rainfall, you can use this relationship for whatever duration in continuous time.
The time of concentration is the last one?
Okay, it's the last one, but let's suppose, I said this before. I said, strictly speaking, if you want to be very rigorous in this definition, this relationship doesn't have any mean for longer times than the time of concentration. Why? Because this delta A is defined for a time until the time of concentration. Okay? Because, of course, if your time of concentration is 4 hours, then you can define A1, A2, A3, delta, A4. And then it's not meaningful to say I use this relationship for computing rainfall after 5 hours, river flow after 5 hours, because one cannot compute delta A5. Doesn't exist. But if you want to make it general, you just need to assume that delta A5 is 0. And then you can use this relationship here. Which means that when you get a rainfall that is occurred more than 5 hours before, more than 4 hours before, more than the time of concentration before, it is multiplied by 0. So it's not effective. So again, if you want to make this relationship general, for longer times than the time of concentration, you need to assume that delta A5, delta A6, delta A7 is 0. And then you can use this.
Professor,
Yeah?
sorry, about the considerations of the formula. I think you made 3 considerations.
Yes.
The first one you're saying is you need empirical computations to locate the isotones.
Please, I can't really listen. Yeah.
You're saying you made 3 considerations.
Yeah.
And the first one, we need empirical formulations to be able to locate the isotones. And the second
Yes.
one, you're saying it's valid until getting to the time of concentration.
Yes.
And that we need, it's defined on the generality on the basis of the fact that you can start from 0 and have longer durations. The third one, please.
The third one is, you mean it's not included in the list that you made? Okay, let me say then, because I have to remember. So basically, okay, you said that I said that, say again please, the first one is it's linear and therefore it's empirical, okay? And then I made a second consideration and I said you can recognize a mass balance and an energy balance here. This is another consideration that I made. And therefore I said it's an empirical model, but you can recognize that it doesn't contradict the physics. Okay? And then I said this is a relationship that is limited to the time of concentration, but you can make it more general. I think these were the three considerations that I made. Maybe we could look at the video to see if I forgot some. But now, to make it clearer, let me write explicitly, through a summation, how this relationship becomes for time 5. Okay, so let's suppose that we have 5 hours of rainfall, and let's suppose that we want to compute the river flow after 5 hours. So let's see how it becomes. So it would be Q5, and let's remember that the time of concentration is 4. So let's say Tc equal 4, okay? Q5 equal. So there is the summation. So let me say K equal 1 to 5, because T is 5, okay? So let me write it explicitly. Summation of K equal 1 to 5, and then I just rewrite what is written here. Delta AK times I 5 minus K, correct? Yeah. It's, this was, sorry, I didn't notice that. This was T, not N. Do you remember that I made the change between N and T? I forgot to change here. So make the correction, please. Did you correct it? So this is, how can I write the summation to write Q5? Okay, now let me explode the summation. Write down the single terms. So Q5 is equal to, okay, delta AK, so delta A1, which multiplies I4. Correct? The first term. Basically, I'm just writing down the whole summation starting from K equal to 1. So delta AK becomes delta A1, and I5 minus K becomes I4. Okay, good. Now plus delta A2 I3 plus delta A3 I4. 1, 2, 3. Okay, I have 5 terms. Plus delta A4 I4 3, sorry, 2 I1, and these are 4 terms, and so far I am fine. And now I have to write down, I go back here, the last term plus. Okay, the last term is delta A5 0 I 0. So this term disappears. So you see, it works. I0 is not effective anymore. That's fine. Doubts? Now, last addendum. Here I see a problem because, you know, delta t is discrete time. Sometimes I need continuous time. So, why I use discrete time? Because rainfall is usually observed at discrete time. I told you at the beginning, I am drawing the isochrones at the same time steps at which rainfall is observed. But let's suppose that we have continuous measurement of rainfall. We can make this general. So how to transform a summation that refers to discrete time to a continuous time representation? What I need to do is to write, instead of the summation, an integral. That's it. I have to substitute the summation, let me refer to this one, with an integral. I'm not sure it is written here. No, it's not written, but anyway, we can write it down anyway. So let me write Q, depending on t between parentheses, equal integral between 0 and t. Of what? The same thing that I see here under summation, but of course I have to change the symbols because the summation becomes an integral. But it's trivial because, you know, don't be concerned by an integral. An integral is just a summation that instead of referring to discrete time refers to infinitesimal time. But it's the same thing, so don't be concerned by integral. We engineers usually are concerned by integrals. I am. Okay, when I see an integral sign, I say, no, this is something that I can't really well understand. But this is a concept that we should remove. The integral for us, for engineers, is just a summation extended to infinite terms.